Alright, this is Michael D'Agostino, and I'm going to be doing some synthesis example problems from Chapter 12. This is question 2. Give a sequence of reagents that would affect the following synthetic conversions. Each problem requires at least 2 synthetic steps. We're going to be going all 4 of them, and we're going to be doing them pretty quickly. So let's get started. So the first thing we need to do here is we need to do an epoxide reaction to be able to get the trans epoxide as a product. So the first thing we need is a double bond, and to get that we need to do an E2 reaction using this. So here's the mechanic. The electrons on the oxygen will push off the hydrogen, the bonds will collapse and form a double bond and kick the bromine off. That'll leave us with a double bond. So the next thing we need to do is we need to get our epoxide, and we're going to use this to be able to get to it. Here's the whole mechanism behind electron pushing, but basically we're sticking an oxygen onto the double bond. So now what we're going to do is we're going to use hydroxide to open up the epoxide and form our final product. And we're using this specifically because we need the trans. Here's the process behind that. The oxygen will grab onto one of the hydrogens. It'll then form an alcohol, which will then open up when we add the water. And we end up with a final product of a trans-racemic mixture over there. So now we have to do this reaction. We need to split this thing into 2 other things. And to do that, we're going to need to do an alkene and ozonolysis reaction. So we're going to start by doing an alkene synthesis reaction. And to do this, we're going to use an acid, sulfuric acid, and a little bit of heat, because with heat we can force the E1 mechanism. And this is the full mechanism right here. The electrons on the oxygen will attach to the hydrogen, which will then push the alcohol bond onto the oxygen in the acid. We're then left with a water molecule that'll be kicked off by the carbon, and the bond will then collapse to form a double bond. Next, we're going to do an ozonolysis reaction, and here's the first step, which forms our ozonide. This is the process behind getting there. This will split into 2 molecules, it'll flip itself around and then reconnect, and then we end up with that thing on the right. So next we're going to need a way to split this into 2 molecules, and we're going to use water for this. The zinc is there because we're going to end up with a byproduct of hydrogen peroxide, and we need to reduce that. So here's the electron pushing mechanism. That'll eventually split it into 2 with the water molecule. And here's the further reaction with another water molecule. And then that gives us our final product when we rearrange it. Next up, we have this alkyne, and we need to turn it into an alkene. So to do this, we're going to do an alkyne alkylation and reduction. So first we're going to use NaNH2 to be able to take our hydrogen off of the alkyne. Our NH2 will come in, the electrons will grab the hydrogen, and the carbon-hydrogen bond on the end of the alkyne will move onto the carbon, and we'll be left with electrons on the end. Next, we're going to need to attach a methyl group there, so we'll use methyl bromide. The process for this is simple. The alkyne electrons will attach onto the methyl group carbon, and the methyl bromide bond will get kicked off onto the bromide. And we'll be left with a bromide out there and our methyl group attached to our alkyne. So the next thing we need to do is convert this alkyne into an alkene. And to do this, we're going to use sodium and NH3. So the process for this is an alkyne reduction. 1 sodium electron will attach to the end carbon, and it'll kick an alkyne bond onto the original carbon. And that'll leave us with this very unbalanced mixture. And with a little bit of electron pushing, we can have one of our groups grab a hydrogen. The hydrogen NH2 bond will then get kicked off onto the NH2, and the spare sodium electron will be pushed onto the end carbon. And we'll end up with something like this. We'll have a hydrogen attached to our innermost part of the compound we're working with, and we'll have 2 electrons on the end carbon. Next, we just need to be able to attach a hydrogen, and we'll use another NH3 for that. The electrons on the end, carbon, will grab the hydrogen, and again, the hydrogen NH2 bond will get kicked off and onto the NH2, and we'll be left with our final product after that, with 2 hydrogens attached to the double bonded carbons. Next, we have this cyclopentane ring with a methyl attached. The first thing we're going to want to do is a bromination reaction. We'll do this using bromine and UV light. So the UV light will split the bromine-bromine bond and put 1 electron on each. And with a little bit of electron pushing, we can have 1 hydrobromine molecule floating, and we can have 1 bromine attach itself to the cyclopentane ring, and we'll be left with that final product right there. So what we need to do now is we need to get a double bond on a cyclopentane ring. And so to do this, we need to do an E2 reaction. And we'll be using NaOCH2CH3 for this one. So the bond between the second carbon and the hydrogen will get kicked off and it'll form a double bond. And the electrons from the carbon-1 bromine bond will get kicked off onto the bromine and we'll be left with a floating bromine ion. And we'll be left with this product right here, a double bond between carbon 1 and 2 and a methyl on carbon 1. So the last thing we need to do is a hydroboration oxidation reaction. 2 steps included as one here. BH3 and THF as step 3, and NaOH with hydrogen peroxide, step 2. So we're going to attach our BH3 molecule, and it'll come in as a transition state on one side of the cyclopentane ring. And because of this, it'll actually attach itself onto one of either sides of the cyclopentane ring, which will leave us with a racemic mixture in the end. And that's all for this video. Hope you enjoyed.